Welcome to the Problems channel, season 3, episode 19, the episode which I titled A Creative Swap of Two Subarrays, because in this episode we will find a creative way to swap two subarrays whose size is fixed and given ahead of time, honoring the big O of one space complexity. But before we deep dive into the underlying mathematics of this problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, by all means do ask. The best way to ask your question is to find an episode that is of interest to you. Use the comment section under that episode, and I will do my best in order to find the time to answer all of your questions. And of course, I would like to extend my deepest gratitude to all the current supporters and current subscribers of our channel, and especially the people whom I know personally from Quora. The objective of the computer science problem number 4 of the season number 3, as is shown in the upper left corner of your screen, season 3 computer science problem number 4, is to find a creative way or a creative line of reasoning for swapping two subarrays whose sizes are fixed and are given ahead of time. That is, let us assume for demonstration purposes on the input into our creative solution of this problem, we're given an array that is partitioned into two subarrays, the logically left subarray and the logically right subarray. The logically left subarray is represented, let us say, by yellow squares whose contents are 1, 2, 3, 4, 5, 6, 7, and the contents of the right subarray are represented by the blue circles whose contents are A, B, C, D, and E. Consequently, the size of the left subarray is 7 elements, the size of the right subarray is 5 elements, and the overall size of this array is 7 plus 5 is 12 elements. And if that is the partition of the total array into the left and the right subarrays, then on the output of our creative algorithm, the 7 yellow squares that used to be on the left of the input array now must percolate or gravitate to the right side of the output array, but they must do so in exactly the same order in which they were present in the input array originally. That is, the contents of the yellow squares must still be 1, 2, 3, 4, 5, 6, 7 in that order. And likewise, the formerly right subarray represented by the blue circles must now percolate from the right to the left, but honoring the input order of the elements in this subarray. And this now left subarray should have the following contents: A, B, C, D, and E. All these manipulations must be done in such a way that they are carried out in place or honoring the big O of one space complexity. Even though at first blush what I'm about to say may come across as silly nonsense, the attentive members of our audience should really pay attention and take this idea seriously, because no matter how naive this brute force wishful thinking may come across, this is actually a viable way to start solving technical problems, and quite often such an approach is exactly what helps us get our creative juices flowing, and that eventually leads to a solution of the problem. That is, as a conceptual overview, what are we required to do in this problem? A conceptual solution of this problem gives us several combinatorial options, of which one is the following. Let's say we again conceptually lift the left sub-array represented by 7 yellow squares, and in the vacuum that is left, we shift the right sub-arrays, the 5 elements represented by blue circles, and then take our yellow left sub-array that's floating in the air right now. We also shift it appropriately, and then we drop it where it's supposed to be, and voila, we have our 2 sub-arrays swapped. Likewise, we can do the following. Instead of lifting the left sub-array, we can equivalently lift the right sub-array up in the air into the formed vacuum. We shift the formerly left sub-array, then we take our right sub-array that is hanging in the air right now, we shift it appropriately, and then we drop it in place, and voila, our problem technically is solved. In other words, we now understand that conceptually what we are required to do is the so-called lift and shift. Now that we understand that conceptually what we're required to do is lift and shift, how this lift and shift idea can be implemented in practice. Well, here some of the members of our audience who, like me, professionally 9 to 5 have been writing C code for many decades will no doubt come up with the following memmove idea. And the memmove is the C runtime library function from section 3. If you do memmove, this will come up, section 3 explanation of the prototype of this function, and it is designed to handle overlapping memory addresses correctly, which is the flaw that is available or that is present in the memcopy memcpy function. In other words, we use memmove in all possible cases, and in this particular scenario, 2 memmoves will solve our problem, provided that we have some room available to us, let's say to the left or to the right of the input array. How will that work? Well, let us assume, for example, that L, with L, we designate L will be the size of the left sub-array, and in this case, that size is what? 7. So let's assume that we have L units of memory located to the right of the input array. The first memmove, we do not really have to move the entire array, we just have to memmove the left sub-array. So the first memmove will move the L, or 7 in this particular case, units of memory to the right of the array at the end of it, and then that will be the first memmove. And what will the second memmove do? The second memmove will move the entire but already swapped array, L plus R. Let's say here R is the size of the right sub-array. In this case, it will be 5. Then we move R plus L units of memory all the way to the beginning, and voila, we will have our 2 sub-arrays swapped as required, which will also honor the input order of the elements in each sub-array. Likewise, there are other variations once you understand how that works. For example, let's say we have, it so happens that we have R, or 5 units of memory appropriately sized to the left of the input array. In this case, the first memmove we'll move this chunk, this sub-array, to the left of the input array, and then the second memmove will move again the entire size, R plus L, the entire chunk of memory, into position so that we now have our output array occupying the space that was in the input array, but the sub-arrays are now swapped and the order of the elements in each sub-array, A, B, C, D, E, and 1, 2, 3, 4, 5, 6, 7 is honored. Of course, this is not really a solution. This is technically a hack, because in this case we are thinking as computer programmers, not as computer scientists. And this is also a hack because this hack does not honor the space complexity of O of 1 requirement. We demand that we have extra room or extra space, appropriately sized, of course, on either the right extremity of the input array or on the left extremity of the input array. However, our requirement is that this transformation happens in place, honoring the big O of 1 space complexity, and it is actually not a pure nebulous academic requirement. Quite often in practice, and in my practice, in my experience, in my professional career, I've seen it a number of times. When we have to operate strictly within the constraints of a tight, fixed size memory box, and there is no way we can allocate more or use memory that is located to the right or to the left of the input array, even though many times there is memory to the left and to the right of the input array, but the problem is that that memory is occupied by other information and it cannot be trashed, it cannot be overwritten with the memmove solution, and that means that we have to think harder. Now that we have shook all the hacky stuff out of our system, we take off the head that reads a computer programmer and we put on the head that reads a computer scientist, and we begin thinking algorithmically. And here many students will come up with the following solution that honors the first requirement, that the transformation that we're after is in place, or honors the big O of 1 space complexity, which means that we are not allowed in our algorithm to allocate any significant chunks of memory. Many students will come up with the following idea. First, for example, we can reverse in place individual sub-arrays one by one, and which one we start with, it doesn't really matter. Here we have combinatorial options. Let's say first we reverse the individual left sub-array, and instead of the elements in the sub-array being in the original order 1, 2, 3, 4, 5, 6, 7, we know the algorithm. We swap diametrically opposite elements of this array and we move inward towards the perceived or logical vertical axis of symmetry of such an array. In this case, for example, it means we swap the elements 1 and 7, 2 and 6, 3 and 5, and the element number 4 remains stationary or fixed, and we put the elements in the left sub-array in reverse order, or the order 7, 6, 5, 4, 3, 2, 1. Likewise, we do the same thing with the right sub-array, and we take the elements A, B, C, D, E. We swap them with respect to the perceived vertical axis of symmetry of this sub-array. We swap the elements A and E, B and D. The elements here remain stationary, and now after this individual swap of R or 5 elements in the right sub-array, they go in the order E, D, C, B, A. This is the first step of our algorithm that honors the in-place requirement for the transformation. And then what do? Well, then we apply the same idea, but to the entire array. And we now reverse the elements in the individually swapped array or the intermediate array. And in this case, we take the entire array, we find its perceived or logical vertical axis of symmetry, and with respect to this axis of symmetry, we keep swapping the elements. For example, here we swap the element 7 with the element A, the element 6 with the element B, 5 goes with C, and so on. And now we have our problem solved. The formerly right subarray percolates to the left extremity of the output array, honoring the input order of the elements A, B, C, D, E, and so does the formerly left subarray, which now becomes the right subarray, which also honors the input order of the elements in that subarray 1, 2, 3, 4, 5, 6, 7. But this is not the only way. Another option over here, again, this is just a minor adjustment. Instead of first reversing the elements in the left subarray, we can do that. We can reverse the elements in the right subarray first, then reverse the elements in the left subarray, and then flip the order of the entire array. Or we can do the same operation in reverse order, so to speak. First, we reverse all the elements in the entire array by trading the elements with respect to the perceived vertical axis of symmetry of that string, if you will, or that array, and then we exchange the elements, for example, E and 1, then D and 2, and so on. And in this case, the formerly right subarray percolates to the left extremity, and the formerly left subarray percolates to the right extremity of the intermediate array, with the exception that the order of the elements in the subarrays is still reversed. And what do we do next? Well, next we reverse the elements in the individual subarrays, but this time we have to remember that if we flip the order of the elements in the entire array first, remember the designations L and R for the sizes of these subarrays, now flip. We now have R elements to reverse on the left side of the intermediate array, and we have L elements to reverse on the right extremity of this intermediate array. And once we do that, we put these elements in the requested order A, B, C, D, E on the left, and 1, 2, 3, 4, 5, 6, 7 on the right. Problem solved. Honoring the in place or big O of 1 space complexity, we do so without allocating any major chunks of memory. We only need a frame variable that will temporarily hold the enough amount of memory in order to do the traditional swap, but this is about it. This is a perfectly valid solution. However, even though this is a solution that honors the in place or big O of 1 space complexity, this solution is not creative enough. And if you solve this problem this particular way on this channel, the most you can count on is a solid C plus for a mark. Let's say this is definitely not an A. On this channel, you have to be much more creative. And even though many students will come up with this problem, the next idea that we will discuss is unfortunately not visited by too many students. There are two goals of this segment of this episode. The first such goal is to demonstrate the fact that solving as many different problems in as many different layers of mathematics is only beneficial, and not only in mathematics but in physics and computer science, because when we do so, we step into the meta arc of solving technical problems, and while we are under that arc, we may get the feel for the flow, for the beat, and for the fabric of technical solving problem. The second goal of this segment is to bring front and center the matters of human creativity, because evidently you do not have to manipulate the research or PhD level mathematics in order to be creative in mathematics, physics, and computer science. And it is possible and difficult to be creative, even if we manipulate just baby level or, let's say, middle school mathematics, because when I will tell you the mathematics behind this creative solution that you were expected to generate, you will say, oh, gee, of course I know that fact. But the thing is, even though many students do know about the fact that underlines our creative solution, not that many students can connect the knowledge of mathematical unit of information that they possess with what is required, and that is precisely the crux of the matter of being creative. That is why I will not go into all the gory details of the motivation of the upcoming solution, because in season 1, episode 7, under the guise of the mathematical problem S1M8, it was the mathematical problem number 8 in season 1, we discussed that solution in great detail, and those of the members of our channel who joined us lately and missed this episode and the solution of this mathematical problem are encouraged to use the season guide, find that episode and watch it at your leisure, and perhaps do that first before moving on, because here I will only tell you the gist of the mathematical problem S1M8. In that problem, we were given a 3x3 chessboard, black squares, white squares, two pairs of opposing colors chess knights, two black chess knights, two white chess knights, and the objective of this problem was to swap the positions of these two pairs of knights in the smallest number of moves, that is, in the smallest number of moves. Using the legal chess knight moves, we are to put these two black knights in the bottom row and these two white chess knights into the top row, swapping their positions. And if you will try to solve this problem in any which way, haphazardly, without any guidance, I pretty much guarantee you that you will have a very rough time doing so. In season 1, episode 7, when we were studying the mechanics of the transform and conquer problem solving approach, we solved that problem using precisely that approach, transform and conquer, and the transformation that unlocks an elegant solution of this problem was the following: number the squares of the given 3x3 chess board in a way that follows the legal chess knight moves. Since evidently the center square of that 3x3 chessboard is not reachable by any of the knights, we leave it alone, we forget that it exists, and then which square we use to start doesn't really matter. I used the traditional upper left corner, and if we mark this upper left square of the 3x3 chessboard with 1, then the next legal move of the chess knight will be which one? This way and this way. So this square becomes 2, 3, 4, 5, 6, 7, 8, 1 closes the circle. And if we connect these consecutive numbers with, let's say, rubber bands, then the magic transformation that is tactically advantageous is the following. We grab these numbers, and using the fact that these numbers are connected to their neighbors with rubber bands, we unstretch these rubber bands. 2 goes into 6, 6 goes into 2, 4 goes into 8, 8 goes into 4, and voila, what do we have? We have a nice circle, or a virtual chessboard. But the thing is, the tactical advantage of this virtual chessboard or transformed chessboard is the following. The mysterious, seemingly unnatural, and not really following any rhyme or reason, zigzaggy motions of our chess knights on the traditional boards all of a sudden become smooth, because all we have to do is move our chess knights one by one in circle. And because in this formation there are no gaps and the numbers are ordered consecutively, this pretty much guarantees the smallest number of steps that will swap the chess knights as requested. And that motion will also guarantee the swap. Not only it will guarantee the smallest number of steps, but it will guarantee that the swap will happen if we move our chess knights over the circle, let's say over here in this direction, 1, 2, 3, 4, 5, 1 at a time, then eventually our chess knights will percolate into their final home positions, and these positions will correlate to the problem that is in the solved state. The black chess knights will be at the bottom, the white chess knights will be on the top. Just to demonstrate you again in several seconds or less, the mechanics of this solution is the following. On the virtual board, our chess knight that sits in the position number 1 goes into position number 2. The chess knight, the black knight that sits at the position 7 goes into the position 8. The white knight in 3 goes into 4, and the white knight in 5 goes into 6. So this is the circular chase, smooth motions, but once we understand these motions, we go back to the actual board and say, aha, the black knight goes from 1 into 2, and this guy goes over here. The black knight in 7 goes into 8. So 7 goes into 8 over here. You see, this is already some weird, unnatural, and mysterious zigzag motions on the board. And if side observer looks just at these motions, that observer will have no chance, no other choice but to wonder, where did this come from? But the motion on the circle is smooth. 3 goes to 4, so 3 goes to 4 over here, and 5 goes to 6, so 5 goes to 6 over here. You see, this is how these things work. And now, once we keep moving these chess knights one at a time, one step at a time, we basically trace our smooth circular evident or obvious motion with the mysterious zigzaggy jumps. But at the end, in the finite number of iterations, our chess knight eventually will percolate into the square number 5. This guy will be in 3, this guy will be in 1, and this guy will be in 7. Voila! Chess knights swap their position in the shortest number of legal moves. Game over. What is the lesson that we learn from this motivation or from solving this particular problem? The lesson that we learn over here is the following. Somewhere in your problem there is a circle. Find that circle, put the local object on that circle, and solve the problem by moving your objects over that circle. And admittedly, when in vacuum we stare at a pronounced, let's say, squarey situations where we have a big square made up of small squares, it is not really that evident where is that circle, because the motions of the chess knights is also L-shaped, zigzaggy. It doesn't really lend itself naturally to dealing with the circle. Yet we now know that a tactically advantageous circle was or is there all along, and the challenge is, the intellectual challenge is to find that circle and put it to our advantage. And this is exactly what we will do in the problem where we're required to find a creative way to swap two subarrays. The mathematical underpinning or the mathematical foundation of our creative swap of two subarrays is the following middle school theorem. Let us assume that two straight lines, A1, shown over here in light blue, and A2, shown also in light blue, belong to one and the same ambient plane, and they intersect at a point, let's say O, in such a way that they form a non-trivial angle theta, shown in blue over here and over here between them. Then the claim of our theorem is the following. A composition of two consecutive reflections of any point in the parent plane is equivalent to the rotation of that plane about the point O, the point where the two given straight lines intersect, by twice the angle theta between these straight lines. So more or less symbolically, we can capture this theorem the following. If two straight lines A1 and A2 intersect over a single point, in general, two straight lines in space are under no obligation to intersect. For example, the appropriately chosen edges of a regular tetrahedron sit on the straight lines that are skewed. They do not intersect. But if two straight lines intersect, this is the situation we're interested in. And let's say the angle between these two straight lines, shown with a cap over here, is theta. Then the conclusion of this theorem is the following. If a sample point P, that is evidently in the general case, does not sit on any of these straight lines, is reflected into the point P1 in the straight line A1, and then that point P1 is reflected into the point P2 in the straight line A2, then the rotation of the parent plane or of the point P about the point O, where the two straight lines intersect, by twice the angle between them, 2 theta, is equivalent to this reflection. In other words, that will produce the point P2. Visually, we take our point P that belongs to the ambient plane. We reflect it in the straight line A1 into the point P1. Then we take that point P1 and right away reflect it in the straight line A2 into the point P2. And that is the meaning of the mathematical operation known as a composition, where the output of the previous operation becomes the input for the next operation. We thus produce the point P2, and the claim of this theorem that after this composition of reflections, if we rotate the parent plane in the appropriate direction about the point O by the angle twice theta, we will put the point P precisely on the point P2. And of course, conversely, these things work in reverse order. And the proof of this theorem you should be able to generate on your own. It is very straightforward, no specialized knowledge, and this proof is based on the mechanics of this geometric transformation known as reflection. How do we reflect the point P in a given straight line, let's say A1? We construct a perpendicular to the axis of reflection A1 through the point P. This perpendicular will intersect the axis of reflection at the point, let's say another point. I do not want to pollute our namespace with more names than I have to. You understand what's going on. This will be the point where the perpendicular to the axis of reflection through the given point P intersects that axis of reflection, and this distance right here, well, let's use the red chalk. This distance right here will be equal to this distance. In other words, on this perpendicular, we, let's say, draw a circle that has the center at this point. The radius is this distance. We locate the point P1 on that perpendicular, and boom, voila, we reflected the point P in the straight line A1. Likewise, we repeat the same steps again. We draw a perpendicular to the second straight line A2 through the point P1. On that perpendicular, we construct another line segment that has this length over here, obtain the point P2, and off we go. So for the proof, what do we observe? Well, we see that by construction, by the mechanics of reflection in the straight line, and even though on this channel I have a course that explains or introduces the students who are willing to learn about this, the mechanics of the reflection in a circle. Here we reflect our plane not in the circle but in the straight line, and this is how these things work. And due to the mechanics, we have which line segments equal in length. Well, this line segment is equal to this line segment. All right angles, remember, are equal by magnitude, and we have this side over here, this side, shared across which triangles? Well, this triangle, I will lightly hatch it in this triangle, two smaller triangles, you see, these two triangles. So by side, angle, side, side, angle, side, these two triangles are what? They are congruent, and that means that the corresponding angles and the side lengths are equal. That means that this distance PO is exactly the same as the distance P1O as well. And what do we call this geometric object which honors the following observation? The distance from any point on that object to a fixed point is one and the same. Well, that object is called a circle, and this is the circle shown in white over here. Likewise, by the same exact technology, we prove that by side, angle, side, and side, angle, side, these two smaller other pair of triangles is congruent. That means that the distance P2O is the same as P1O, which is the same as PO. So all the points P2, P1, and P are equidistant from one fixed point in the parent plane, the point O, and that means they belong to what? They belong to a circle. And now the final technical observation of this theorem, twice the angle theta between the intersecting straight line. Where did it come from? Well, this is very straightforward because the triangles are congruent. We have angle theta 1 shown in green, theta 1 shown in green, and theta 2 shown in blue, and theta 2 shown in blue. So what is the angular displacement of our point P with respect to the point O in the chosen direction into the point P2. Well, that angular displacement is given by what? Look at this. Theta 1 plus what? Plus theta 2 plus theta 2 plus theta 2. These are real numbers. Real numbers commute under addition. So we can partition this like this. And what is theta 1 plus theta 2 in this case? Well, this sum is the angle theta, the angle between the intersecting straight lines. And because the real numbers commute under addition, we can yank this theta over here, join these two, theta 1 plus theta 2, and thus we will have what? Theta plus theta, which is what? 2 theta, theorem proved. And this is exactly what we will use for our creative swap of two sub-arrays. If you're still not catching on to the direction in which our creative solution will go, now is the good time for you to put this video on pause, walk away, think about this solution on your own, and then come back and compare your ideas to ours. As such, a creative solution that you were expected to generate on your own and a solution that will earn you a solid A on this channel is the following. We take our finitely sized linear container, an array, and we curl it into a circle. Technically speaking, let's say we grab our array and fix it by the first element of the input array. We curl it up and bring up the final element of this array closer to the first element, and we do so in such a way that all the elements of our array are now represented by the vertices of a regular polygon on n vertices, where n is equal to, let's agree n is equal to L plus R, where L is the size of the left sub array, R is the size of the right sub array. As such, we now have a regular polygon on L plus R vertices, and that means that the angular displacement between any two immediately adjacent vertices or elements of our input array is one and the same. Now that we made that crucial creative step, what do we do next? Well, next we, let's say, take our circle or our polygon by the first element. Let's say, for example, it doesn't have to be that way, but let's, for ease of computational purposes, we grab it by the first element of the right sub array, for example. We grab our polygon and we rotate it in the parent plane about the center of the circumcircle, let's say, by the appropriate angular measure, and put that element, A, in this case blue circled A, into position where yellow squared 1 used to be. And because rotation of the plane is what's called a motion in mathematics, or a rigid motion, that means that all the material on that circle will rotate in exactly the same way. And after that rotation is complete, which is shown by the blue arrow over here, and technically or conceptually I showed this rotation with the white arrow, rotation by the angle shown over here with the blue arrow, we will have the configuration of the objects shown on the right. In other words, here we will have our elements on the circle sitting in which order? A, B, C, D, E, 1, 2, 3, 4, 5, 6, 7. And what do we do next? Next, we take our mathematical scissors and we cut the mathematical umbilical cord, let's say, over here, that connects the last element now of our formerly, let's say, left input array to the formerly right input sub array. We straighten our circle into a straight line, again into the original linear container, and voila, as if by magic, what do we have? We have exactly the linear container that has its elements ordered A, B, C, D, E, and then 1, 2, 3, 4, 5, 6, 7, problem solved. And this is also done in place. We will do that manipulation in place. Now, many people will say, oh, gee, we know about this middle school theorem that two consecutive reflections in two intersecting lines amount to a rotation. But that is exactly the crux of the matter of, well, at this point, it's relevant to say human creativity. In other words, to be creative, you do not need to manipulate PhD level or research level mathematics. Even this is also always welcome, but it is possible to be creative even by manipulating baby middle school mathematics. And this problem hopefully shows that it is difficult to do even just that. Even manipulating baby mathematics in a creative way is a challenge already, as is evident by this solution, because unfortunately not that many students do come up with this idea and generate this idea, even though, again, pretty much all the students already know about this theorem. So the crux of human creativity comes to connecting, or the ability to connect, the unit of mathematical knowledge that you already know to what is needed. And this also shows that, again, in order to succeed in computer science, you better know your mathematics, because computer science is nothing more than a specialized applied mathematics. Just like if you want to succeed in theoretical physics is its own separate, let's say, branch of applied mathematics. Either way, theoretical physics, computer science, they sit on the foundation of mathematics, and that is why it is beneficial to know that mathematics. Either way, the idea that I wanted to portray in this segment is that human creativity is the task of, or one of the facets of human creativity is the ability to connect the units of mathematical knowledge that you already know to the task or the objective at hand. And now that we understand what needs to be done, again, this is a conceptual solution. Now we know that a rotation of the plane is what? Well, this is a composition of two reflections. So all we have to do right now is throw two axes of reflection on top of our regular polygon and observe that reflections of the elements of array in an appropriately positioned axis of reflection is what? Is basically a mere swap of two elements. Let's say A sub k and A sub j. In the swap, this element goes in this direction. Let's say this element goes in this direction, and all the battle that will unfold in the next few seconds will rotate, or let's say circle around, determining what these coefficients k and j are, and this is it. Before we step up to the actual implementation of this creative idea of swapping two sub-arrays, I want to say a few words. These words are optional. You don't have to listen, but if you do not know anything about it, then in college at some point you will have to learn, and you will learn about this. The congruence motions of a circle, known as rotations of the circle in the parent plane about its center by the angular measure taken from the following subset of real numbers, 0 inclusive and 2 pi exclusive, coupled with the operation of composition of one rotation followed by the other, and the angular measures for these rotations taken from this subset of real numbers, formed the so-called infinite commutative group, because the rotations of the plane, unlike the rotations of the space, are commutative. In other words, the rotations of a sphere about its center in general are not commutative, but in the plane things work out quite pleasantly. The rotations of a circle about its center in the parent plane are commutative. And in this case, there are uncountably infinitely many real numbers sitting in this particular subset of real numbers. Consequently, this group is infinite, and in some sense, intuitively, we can say that within these boundaries, the rotations of the circle are smooth, or let's say continuous by any real number. Now, the so-called dihedral groups, Dn designated with Dn, they can be generated in a number of different ways, and one popular way to generate these dihedral groups is by the congruence motions of regular polygons, such as, let's say, an equilateral triangle, or a square, or a regular pentagon, a regular hexagon, and so on. These groups have a well-known structure. They have a subgroup that contains the group of rotations, congruence rotations, and the entire group includes this subgroup of rotations and the motions known as reflections in the axis of symmetry. But like we know already, remember, two reflections into intersecting straight lines generate what? A rotation. That's why the congruence motions known as reflections of regular polygons, they do not form a subgroup, and so on. And these dihedral finite dihedral groups, Dn, can also be generated by the congruence motions of three-dimensional objects known as pyramids. The base of such pyramid must be a regular polygon, and the apex or the vertex of that pyramid must project directly dead onto the center of such a shape. And congruence motion in either case is a motion that takes a given geometric shape back into itself. And in this case, these congruence motions correspond to discrete, so to speak, again, intuitively speaking, discrete angles or specific angles. And what are these angles? This is precisely what we need in our problem. These angles come from the following idea. Any two immediately adjacent vertices of our regular polygon on n vertices are seen from the center of that polygon under what angle? The central angle theta c. I call it theta c, where the subscript c stands for central angle, the smallest central angle. And the magnitude of that central angle is what? Well, evidently is 2 pi over n, or in our case, 2 pi over L plus R, where L is the size of the left subarray, R is the size of the right subarray. All is good. In our case, this L plus R, 7 plus 5 is 12, 2 pi over 12 is pi over 6. Let's say 30 degrees if you want to do the numbers, and you should really trace these constructions with your favorite graphing software. But now recall that our rotation of the regular polygon that solves the problem is done by how many units of this theta c? Well, we already see that we have to rotate the node A into the node 1, and how many such central angles do we step through? 1, 2, 3, 4, 5, or precisely R. Consequently, the rotation angle, see that we have to be careful over here, not the angle between the straight lines that solves the problem, but the rotation angle theta R, that's why I gave it the subscript R, is basically R copies of our central angle theta C. So that is 2 pi times R over L plus R, in our case 5 pi over 6. You do the numbers, and then now we come to the point that is the crux of our solution. Theta S for the solution angle between the intersecting straight lines that will play the roles of axes in which we will reflect our curled up into a circle array must be what? Remember that two reflections correspond to a rotation by twice the angle. So our solution angle theta S between the intersecting straight lines must be theta R divided by 2, which is theta C divided by 2 times R, pi times R over L plus R, in this particular case 5 pi over 12. But the important thing to realize here is the following: precisely because our angle between the intersecting straight lines in which we will be reflecting the elements of our array curled into a circle is an integer or integral multiple of 1/2 of the central angle theta c over 2. Because R, why? Because R is an integer. It's actually, in general, it should be a strictly positive whole number. So integral multiple of 1/2 of the smallest central angle between any two immediately adjacent vertices of a regular polygon, which is two adjacent elements in our array, is cut in half. And that means that in general, and of course, because again, all the elements of our area are sprinkled over the periphery of our circle uniformly, these two reasons explain why, in general, the actual position of our axis of reflections, A1 shown in green, and in the next segment I'll show you the second axis, A2, is irrelevant. We can place this axis any which way so long that that placement allows for a meaningful application of reflection. So in other words, our axis has to obviously pass through the center of the circumcircle or the center of our regular polygon on n vertices, and it should either pass strictly in between. In my mostly hand drawing, it doesn't look that accurate. Once you do the constructions with graphing software, it will look nice and neat, but this axis has to pass either through the middles, middles of any two adjacent vertices, and this takes care of this 1/2 of the central angle. You see integral multiple of 1/2, or our axis will pass through any two, for example, two vertices of the regular polygon, and that is how we need to choose the specific location of our axis. And because we're in charge, we're in control for the placement of the first axis of reflection, which I still name A1, we can always place that axis of reflection between the first element of the left subarray and the last element of the right subarray. For my demonstration purposes, that will be this axis of reflection number 1, A1, will be placed strictly in between, in the dead middle of the nodes 1 and E, the yellow square 1 and the blue circle E. I apologize for a small font because here in the next segment I will be drawing another circle over here in order to show you what happens once we execute the second reflection. But in the first reflection, as a result of the first reflection, what will happen? Our first axis of reflection, A1 shown in green, runs between the nodes 1 and E, and on the far side, 6 and 7. Obviously, it passes through the center of that regular polygon. So that means that for the first reflection, we will be reflecting nodes in that straight line. But computer science, from the computer science perspective, we will be swapping the elements of the array with respect to that axis of reflection. In other words, after the first reflection, we will be swapping the elements of the array 1 and E, 2 and D, 3 and C, 4 and B, 5 and A, 6 and 7. And once that happens, I depicted this swapped nodes in the outer circle. This is the circle over here. Maybe I can highlight it a little bit more, but you understand what is going on. Again, I apologize for not being too precise. It's difficult to be precise, but you understand conceptually the idea of what is going on. Geometrically, we swap, for example, the nodes E and 1. It means that proportionally the node that was E goes over here, and the node that was 1 goes over here. So 1 and E. You see, proportionally. Again, when you do it with professional software, it will all work out. D and 2 trade places. So proportionally, again, 2 comes where D used to be, and D comes where 2 used to be. You see, that's how it works. It's not complicated. If you have any questions, do ask. The comment section is open. But once we flip all the nodes of our regular polygon, or all the vertices of our polygon in the first axis of reflection, then this is the state of affairs that we will witness after this first reflection. So if we traverse our regular polygon, in this case in the order 1, 2, 3, 4, 5, 6, 7, A, B, C, D, E. This is the order in which the input sub-arrays are given to us. Then in the same direction, we will have the nodes sitting on our circle as follows: E, D, C, B, A, 7, 6, 5, 4, 3, 2, 1. And now you don't really have to remember these formulas. You should be able to deduce them yourselves. It's not really complicated, but I'll give you a chance to put this video on pause, copy these formulas, or rewind, come back to this particular part in this segment. But in the next segment, I will erase these formulas over here to make room for the second reflection, so we can see how the second axis of reflection should be positioned and what will be the result of reflecting our current elements of the input array in that second axis of reflection. Before we jump into the analysis of what happens after the reflection of the elements of our array curled into a circle in the second axis of symmetry, let us get this out of the way. If you play with the specific numbers for this problem, then you will come up with the following observations. If the total size of the input array, or the sum of the sizes of the left and the right sub-arrays, is a number that is even, then we will have to distinguish two cases. If the size of the right, for example, sub-array is even, and when it's odd. When the size of the right sub-array is even, that means that in this case, since all the numbers are even, the size of the left sub-array must also be even. Then our second array, A2 shown in green, will pass in between two immediately adjacent vertices on both sides of the center of the parent circle, on one side and on the other. And if R, the size of the right sub-array, is a number that is odd, representable as 2k plus 1 for a suitable integer k, then the second axis of reflection, A2, will always pass through two diametrically opposite vertices of the parent regular polygon, or the elements of the input array. And if the size of the input array is a number that is even, that is odd, representable as 2m plus 1 for a suitable integer m, if the size of the input array is odd, then the second axis of reflection, A2, again shown in green, will pass through one node of the regular polygon. That is easy to see that in this case, our first axis of symmetry will always, if it falls between two immediately adjacent, the first, let's say, and the last elements of the array, then it will pass through one element of that array on the other side. And then no matter how many times, you see the solution angle is half of the rotation angle, the integral copies of this half rotation we take, that second axis of reflection will always step on one node of the parent polygon. So once these observations are out of the way, let us see how things work in this specific case. Well, in this case, let me put this over here. We already computed that the solution angle, the angle theta s, in this case will be 5 pi over 12, which is basically 5 copies of 1/2 of the central angle. So here we start with our initial axis of reflection, A1, and we count 5 half central angles: 1, 2, 3, 4, and 5 altogether. 5 half central angles. And that means that in this case, if we look at the intermediate state, our second axis of reflection, shown in slightly different, I'm not sure if you guys can catch that different hue of green, but it's by the looks of it more olive, if you will, green, A2, shown over here, A2, it will pass through the vertices or through the elements of our array named C and 4, 4 and C, through these two nodes and evidently through the center of the parent regular 12 gun, we construct that second axis of reflection, which is rotated with respect to the first one by 5 pi over 12. And what does that mean? That means that the nodes or the elements of our array named C and 4 will remain stationary when the entire plane is reflected in that straight line A2. The element of the array named 4 will be there, will percolate into the outer circle shown over here that represents the final state as 4, and the element of the array named C will percolate into itself. It will remain C in the final state. And then after that, once that is understood, we simply begin reflecting the remaining elements of our array in that axis of reflection A2 shown in green. One more time, make sure you understand what is going on here, and that reflection we will do together. The nodes D and B with respect to that straight line are reflected or trade places in terms of array elements D and B. So D goes into where B used to be and B goes into where D used to be in the previous intermediate step. So B, C, D. Next come the nodes or the array elements E and A. So here we geometrically we reflect the vertices of our regular polygon named E into A and A into E, but computer science equivalent of this geometric transformation is a swap of the elements of the array at the appropriate indexes. So E goes into where A used to be, A goes into where E used to be. And look how beautiful things shake out already. A, B, C, D, E, boom. Our formerly right subarray is about to become the output left subarray, and importantly, in the same requested input order, A, B, C, D, E. Now, what is the next step? Well, next we keep rolling through our we walk, for example, let's say here, technically we walk this way, and in this semicircle we walk this way, and we swap the nodes as we see them. So if we walk our circle this way on that side and this way on that side, after the nodes A and E, what we will see? Well, we will bump into the nodes named 7 and 1. So we swap 1 and 7. We put 1 where 7 used to be, boom, and we put 7 where 1 used to be, boom, 7. So now we have 7 and 1. Next, we keep walking along these semicircles this way towards that side of our axis of reflection. And what do we see? 2 and 6. So 2 goes into where 6 used to be, boom, and 6 goes where 2 used to be, boom. Keep walking. We still have room to go. We still have room to go. The next two nodes we see 3 and 5. So we geometrically reflect nodes 3 and 5 into each other. So 5 goes into where 3 used to be, 5, boom, and 3 goes where 5 used to be, boom, 3. 4 is fixed or stationary element, stationary vertex of our regular polygon, and the game is over. So now that we have our vertices of the regular polygon swapped the second time, technically we rotated the parent plane by the angle twice as large as this angle right here, which is 5 pi over 6. Game over. And as expected, now we again logically cut the umbilical cord that connects these two nodes, and once we straighten them out into the original linear container, voila, we have our subarray swapped. A, B, C, D, E on the left, and 1, 2, 3, 4, 5, 6, 7 on the right as requested. And look at this. Again, it may not be that evident because here we mostly do this visual manipulation that corresponds to geometric reflection. But geometric reflection, as I said before, amounts to the swap of two elements in the array. A sub j goes into A sub k, and conversely a sub k goes into a sub j. And how do we do the swap? Well, we need only one frame variable appropriately sized. AK goes into the temp, AJ goes into AK, and then temp goes into AJ. Boom, game over. So that way we honor the big O of one space complexity requirement, and the problem is solved. The final thing that we have to button up is to look at exactly how will we translate this geometric business of reflecting vertices of the regular polygon in the chosen axis of reflection into the actionable computer science, or in this case, specific computer programming instructions. The last order of business in our creative swap of two subarrays is to understand how to actually carry out the set geometric reflections and how to construct their equivalent in the world of computer science. To that end, here we note that we need to consider two cases when our axis of reflection passes between two immediately adjacent nodes of our regular polygon, which is represented by the elements of the array that we curved into a circle, and when such an axis of reflection passes precisely through the nodes of our regular polygon. As such, overall, our traversal of the regular polygon can be done, or the way I did it is with the help of two indexes. One such set of numbers are captured with the index that will grow. I designated in the code that you can download and look, I designated with the G growing, G and DX growing index. And then the other set of numbers will be captured in the variable called D and dx for diminishing. In other words, we basically cut our regular polygon in half, and again, depending on how this axis of reflection behaves, whether it passes through two diametrically opposite nodes of this polygon or not, we basically cut this polygon in half, and then we maintain two variables. In one, we keep track of the growing index, and with the other variable, we keep track of the diminishing index. And this is it. This is all there is magic to it. Once we have these two indexes, we basically swap two elements in the array at these indexes. Game over. It's not really that complicated. What was difficult in some sense is generating this idea of curling our linear container into a circle, and then recalling the theorem from middle school that the two consecutive reflections amount to a rotation. That was the difficult part. That was the creative part of our ability to solve problems. But once we figure this out, the rest is smooth sailing. It's not really that difficult. And the only caveat here is that in this particular case that is shown on the left side of your board, you will see that we do not need to adjust the number of reflections that we make. We simply cut the size of our array in half, and off you go. The number of reflections in my code, that will be uppercase N, that you will see in a second. That number will be basically the size of the array cut in half. However, when the axis of reflection passes through two diametrically opposite nodes, we need to adjust this number. What do we have to say? We have to reduce this number by 2, because this node and this node of our regular polygon will obviously not participate in the actual non-trivial reflections. These nodes will stay fixed where they are, and we will have to traverse our two halves by the amount of nodes that is by 2 less than the overall number of nodes, for evident reasons, but the idea is the same. With the growing index, we keep track of the indexes that grow. With the diminishing index, we keep the indexes that diminish. And one more caveat over here that I captured on the left side of your screen is the following. I had to come up with my own handmade mod operation, modular arithmetic, from the theory of numbers, because once we, in the theory of numbers, whether the numbers grow or numbers diminish, decrement, the modulus operation works either way. But in the C programming language, admittedly the best programming language of all times, this is not the case. We had to, or at least I had to, write my own custom mod operation function. It returns the corresponding index once we cyclically, see, the idea here is to cyclically increment and cyclically decrement, so we do not roll into the negative numbers when the index that we have to decrease. Obviously, there are no negative indexes in the linear container in the array, so we need to be careful and make sure that our diminishing business does not spill into negative numbers but stays within the boundaries of our box, which is modulus. So the first argument is the index to this function. The first argument to this function is the index to either grow or diminish. The second argument, m, is the modulus, and basically modulus is what? Is the size of the array. It's that simple. And the character up can carry either plus or minus. Plus for grow, minus for diminish. It's not that complicated. You can come up with your convention or whatever, but the implementation of this function is quite simple. If the operation that we're asked to carry out is the operation of growing the index cyclically, all we do is good old number theoretic business. N plus 1, cut it off with m, modulo m. That's it. This is straight from the number theory book. Things work. Everything is beautiful because we increment, and this is the cyclic increment. Now, if the operation that we're asked to do is to diminish the index cyclically, here we have to be careful. If this if statement fails, it means that the operation that we're asked to do is minus, subtraction, or diminish. And here, with the first thing we check is whether the index that we're asked to decrement is already reached the bottommost legal value of 0. If it's 0, if we blindly decrement it into -1, that's not good. That's bad business, bad computer science business. So first we check if n is already 0, we return m minus 1, modulus minus 1. This is the implementation of cyclic decrement. So this way we start again from the end of the array. But here, if the value of the index that we're asked to decrement is not 0, we still have room, so we decrement it by 1, and then we return that value, n minus 1 in this case, m minus 1 in this case, and n plus 1 modulo m in the case of addition, and this is it. Game over. Now, I will not bore you guys with more details than I have you. I think this is enough for you to understand the code that I already prepared for you. If you have any questions, do ask. But the link to the C code that is immediately compilable and that lives in my free GitHub repository is in the comment section to this episode. Click download, if you will, or type it in yourself. It doesn't really matter. The code is ready to be compiled. I tested it several times. It works. Compile, write the code, save it, compile. The instructions are given at the top of that file. And this is it for the computer science problem number 4. Now, as we go through our traditional cycle on this channel, we'll solve 2 problems in mathematics, 1 more problem in physics, and then we'll come back to yet another problem in computer science. So as a fair heads up, the next computer science problem, Season 3, Computer Science 5, will ask you to explain how the shunting yard algorithm works. And then once you understand how it works, we will be asking you to create a slow motion player, preferably using some sort of GUI, graphical user interface. I personally did it using Java, but you can pick anything you like. But here we will complete our discussion of the problem S3CS4, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics S3M11, and The objective of this problem is to evaluate the following finite sum whose common term has the following shape. 1 in the numerator, and in the denominator of that fraction that represents a common term of this finite sum, we have the trigonometric function of sine evaluated at the following argument. Number 2 raised to the power of k, where k is the summation index, times the symbol alpha, where k is a whole positive number that varies over the subset of whole positive numbers 1, 2, 3, 4, 5, and so on, n. And alpha as a symbol represents any real number, subject, of course, to the fact that in this particular finite sum, we can never have the trigonometric function of sine reaching the value of 0. In order to avoid the division by 0, that means that we have a natural constraint on the values of the real number alpha shown over here. This constraint comes naturally from the fact that at multiple or integral multiples of pi, the trigonometric function of sine turns into 0, and this is precisely what is not allowed in this finite sum, hence this constraint. No one in the mathematical community cares deeply about this result, but on this channel we do care deeply about your ability to generate the corresponding convincing, correct, and inventive line of reasoning behind a story of why your answer is what it is, because here evidently we should obtain an alternative expression that looks like a very compact, with a small number of terms, function of what? A function of the real number alpha, subject to the constraint shown on your left, and function of this whole positive number n, because remember, first and foremost, mathematics is an art of telling a story. And if you are not telling a story, you are not doing mathematics. But conversely, if you are telling a story, you may or may not be doing mathematics. And this is exactly what we want to learn how to do on this channel. We want to learn the art and the craft of constructing a story that is mathematical in nature. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my story behind the answer to the problem S3E19.